So as promised, we're going to talk in this video part, we're going to talk about how to use Newton's three laws of motion. So last lecture we went over what they are. I hope that you familiarize yourself with them and can recall pretty quickly in general what Newton's first, second, and third laws are. And now we're going to talk about how to use them, and we're going to do a bunch of examples, which is always helpful for students to go through actual examples. I remember loving when my instructor would actually go through examples. So we're going to do that. But first, we're going to talk about problem-solving strategy. So hopefully give you a roadmap of how to solve all the problems that you need to, or at least how to approach them and break them down a little bit. So this first video here is about problems that involve Newton's first law. And the first challenge is to figure out if Newton's first law applies or not to a problem. So if you come across a problem, how do you know, oh, this means Newton's first law, or this means Newton's second law comes into play? Well, Newton's first law, do you remember what it is? Newton's first law. That's the one that says bodies in motion or at rest. Bodies in motion or rest, stay at rest, unless acted upon. We'll do that. Unless acted on. Yeah? So bodies in motion stay in motion unless acted upon. So unless there's a net external force acting on them causing an acceleration, and bodies at rest stay at rest unless acted upon. So whatever the body is doing, that's what it's going to keep doing, in other words. So that means anytime you have a body in equilibrium, the net force acting on it, so the vector sum of all the forces acting on it, this vector sum is equal to 0. Then Newton's first law applies. So that means it's in equilibrium. So this means two things. Well, it means as many axes as you have. It means that the sum of the forces in the x is equal to 0, and the sum of the forces in the y are equal to 0. And if you have a third spatial axis, then that means the forces in that axis, sum of the forces in the z is 0 also. You don't often encounter those. But at least in these problems introducing, when you first get practice with these. In the real world, there are 3 spatial dimensions, and so it comes up all the time. But it doesn't add too much to help you understand what's going on to add the third axis, so you don't see it as often. So this section is about using Newton's first law to solve problems dealing with bodies in equilibrium. That means this. Some of these problems might seem complicated at first, but they're all done the exact same way, and that's why I'm trying to give you a strategy and a roadmap for how to approach them. And so you can take comfort in the fact that you at least have a way to start breaking down the problem and figuring out what it's wanting. So we're going to talk about that problem-solving strategy next. This is similar to what I had done before with another section. Give you a little bit of a strategy to approach these things. So first, like I said, you have to figure out when you're using Newton's first law. When does it apply? So you must use Newton's first law for any problem that involves forces acting on a body in equilibrium, so either at rest or moving with constant velocity. So if the velocity is constant, it could be 0, may be 0. That means that should trigger in your mind immediately Newton's first law. If the velocity is constant, if it says, oh, it's moving at constant velocity, or a body at rest on a surface, blah, 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 right? If the problem involves more than one body, and the bodies interact with each other, you will also need to use Newton's third law. Do you remember what Newton's third law is? That's the equal and opposite one. So we're just adding more tools to your toolbox, and hopefully if you know when to use each tool, they will help you out tremendously. So there's a number of steps. There's, I would say, 5 steps that you can use to approach these problems. Step 1 is to identify target variables. So target variables. What does that mean? It just means, what are you trying to solve for? So for example, if you're trying to solve for the tension T1, I would just write that. T1 equals something. So then you can just glance back up and remember, okay, that's what I'm solving for, right? Step 2 would be to draw a simple sketch of what's going on. Sometimes these are given to you, but sometimes even when they're given to you, they're a little bit too artistically expressed, and so you can simplify them. So just draw simple sketch. So it might describe to you a situation. It might describe and give you a picture of what's going on, but you can simplify it. So if it says that something slides down a hill, well, you can greatly simplify that by saying, here's our hill, right? It's at some angle that it might give you, and here's that something, right? So it might say like a boulder slides down a hill, not rolls, but slides. Well, the boulder has some mass, and we'll just express it as a box, because that makes things simpler, yeah? And so then you can kind of just simplify what's going on. You don't need to know that there's trees over here and a nice little stream that they've drawn for you. None of that matters. You just draw what matters. So in your simple sketch, you do want to label the things that do matter, like mass and the angles, like I just said, but leave the things that don't matter out. Step 3 would be draw a free body diagram. Free body diagram. And you might need more than one if you care about what's going on with more than one body. And the reason you might care what's going on with more than one body, even if it's only asking about something related to one, is you might need more equations to solve for the thing that you need. And so you might need to consider what's going on with more than one body. But for each body, you would draw its own free body diagram. So no 2 bodies should exist in the same free body diagram. So a number of guidelines I'll read through for making free body diagrams. And you should also read some guidelines that are expressed in your textbook. So ask yourself, what's interacting with the body? So with our ramp and the thing, what's interacting with the body? Well, you might have some friction force, you have gravity, right? And that's about it maybe in that situation. If you had something pulling on it, there'd be something else. We're ignoring whatever we're ignoring, like drag force. Draw a force vector for each interaction. Label each force with a unique symbol. So you shouldn't just have all your forces labeled F, because then you can't distinguish between them, right? So at least do F sub something. And some of them you can do, if you like, you can do T, right, or N for normal. You can kind of give them their own full letter, but some unique symbol that makes sense to you for each of the forces. Draw any angles and label with numeric value if it's known. Label its mass. If weight's given, well, weight is equal to m times g. So if you're on Earth, then you can quickly solve for the mass. If the body is in contact with a surface, you know that there's a normal force, right? So if it's resting on a surface, you know there's a normal force perpendicular to that surface. Even if the surface is sideways like this, the normal force would be perpendicular to it. And there might be a frictional force that's parallel to the surface, right? We're talking about friction, but that would always be parallel to the surface. Keep that in mind. Tension forces come from a rope or a chain or something of the like, and they are always a pull, never a push. If you're trying to push a rope, you'll know why. And it's along the direction of its length. So if the rope is like this, and the body is like this, it's always a force along that direction, pulling on it. It's never pushing, and it's always along the direction of the rope. And you want to make sure you're not making up extra forces on your free body diagram. So you want to, it's actually kind of more common. You might think that there's more things acting on it than there are. And so you want to ask yourself, what causes this force? What is the force? What is causing it? Is it gravity? Is it this rope? Is it the surface or the normal force? What is going on? Is there friction on the surface and that's what's causing it? If you can't name what causes the force, then you might be making it up. It might not exist. And you want to choose an axis for each body and label the diagram with your chosen axes, and that determines a lot of things. So oftentimes if you have a lot of these kinds of forces along, not directly along the traditional up and down route, so this would traditionally be y, this would traditionally be x, right? And this would be in the negative x direction, negative y direction. So you want to choose axes instead that just go along with most of the vectors that you have, most of the forces that you have. So in this case, we might as well do this because you can either have the axes in line with this one, or you can have it along this one. But I'm going to do, oops. Let's see. I'm going to, what am I doing? Group all of this. Maybe it disappears for you, but really I'm just grouping it, so hang with me. I'm going to group it. All right. So if you have forces that are here, 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 and here, these being perpendicular, right? Does that make sense? Perpendicular. It wouldn't make sense to have your axes as I've drawn it, because look at all of these would have to be, we'd have to find the component form of this one, right? The x and y component. We'd have to find the component forms of this one, and this one, and this one. We'd have to find the components of all these different guys, right? That's a lot of work, and we don't really want to do that. You get a sense of what I'm talking about here? So it's a lot of work, a lot of component vectors that we'd be speaking in terms of. But if instead we had our axes, let's see, let me erase the white if I can. Oops. If we rotated our axes, they might work for us better. All right, draw that last one back up there. So what if we rotated and put our axes like this, so they were in line? Well, now 4 out of our 5 vectors are in line already. We don't have to find component vectors of 4 of those. We only have to find component vectors for this guy. And that's it. So we've greatly simplified our problem by doing that. So you really want to choose your axes wisely. Hopefully that makes some sense, because it really helps you out if you can figure out how to do, when to rotate axes and how to choose axes. All right, so then that would be free body diagram, right? That was step 4, or 3. Step 4 would then be to find your equations that you need to solve for your target variables. These equations come from our free body diagram and maybe some other information given in the problem, but mostly our free body diagram. So get back to this color here. So step 4 is, I'll say get equations. Get equations. So this usually means summing the forces in the x, that's something, and setting it equal to 0, because the acceleration is 0, whether it's stopped or if it's traveling at constant velocity, acceleration is 0. And that force is equal to 0. And the sum of the forces in the y, and that's going to be equal to some combination of forces and setting that equal to 0. Yeah? So that's usually your equation. So you have this force minus this force plus this force, some of them might be component forms, is going to be equal to 0 for both of these equations. You have 2 equations then to start working with. And that'll probably get you all the way in a lot of problems. If you need more equations, if this, you get these 2 and you still cannot solve for what you need, then you need to find more equations, and that would mean going to our constant acceleration equations. So 1, 2, 3, and 4 constant acceleration equations, if you remember from a couple videos ago. Otherwise maybe known as kinematic equations. Constant A acceleration equations. Because if the acceleration is 0, and it's always 0, well, that's constant. So you can use those. So the problem may give you information that you can plug in there. It might give you like a starting x position, right, x naught, or it might give you a later x position and an associated time, right? So if you're given some of those things, then you know that you'll probably have to use these constant acceleration equations. And that should get you the rest of the equations that you need. And then, finally, step 5 is the easy part, is you just solve. You do the math. So don't be intimidated. We've already gone 95% of the way through this problem. We have our equations. The rest is just simple algebra to solve for what you need. So you have a system of equations. You might have more than one variable. Most often you will have more than one variable you're trying to solve for, but you hopefully have enough equations that you found to solve for that variable. So that's your game plan. That's your game plan. And then I'll always say evaluate. Because you want to see if what you came up with is reasonable. Both the magnitude and the units, right, and the direction. Okay, so hopefully that gives you kind of a game plan. I'm going to go over an example or two now. So here we have our first problem here. Here it is in words. It also gives you a sketch. So I'm going to throw that up there for you. And I'll get the little sketch that it gives you associated with this. All right, you see that okay? Let's open this up a little more. And then this, put it on here. So I'll give you a second to pause the video maybe and read it. So we're just going to go through our steps. So step 1 is, what are they asking for? So step 1, what are they asking for? They're asking for the tension expressed in terms of W, the weights. Because they're not giving you any numbers here, they're just giving you the situation and some symbols, an angle. So they want the tension in terms of the weight. So I'll do this. Right, so that's step 1. You don't have to write it out, but this at least gives you a game plan in your head. I'll write it out at least for this one, so that you can follow along in these steps as I'm thinking about them. All right. What was step 2? Draw a simple diagram. You might be able to skip this part if they're given this, but I will draw a simplified diagram because I like to do that. Just simplify what's going on. These little lines just kind of mean that's solid. Okay, and then we have this here. We have an O-ring, but it tells you that it has negligible weight, and so we're just going to represent it as like a little particle here. And then it has this as 60 degrees. And then we have another thing there. And so we have T1, T2, T3. This is 60 degrees. And then we have a mass down here. Don't need to draw the engine. Right? So to me, this simplifies it and makes it seem more like a physics problem versus this real world thing where you might be thinking about extra stuff. See, the whole car there is just artistic context. We don't need it. So this is my simplified sketch. So then step 3 would be a free body diagram. In this case, it's helped us by showing in gold that there's 2 separate bodies. One of them doesn't have any weight, so we're considering it to be massless. But it's kind of guiding us to think about both as separate bodies. But let's just start with the engine because it's the most obvious body. So this is step 3, free body diagram. And so free body diagram specifically for the engine. I'll start switching to another color maybe for no particular reason. Engine. So free body diagram, we have weight pulling down on our engine here. I'll do M times G. And we have tension pulling upwards, and it's at rest, it's not falling down or up. And so those 2 vectors ideally in length should be equal. So that's T1. Is there anything else going on with our engine? There's no other forces that I can think of that are acting on it. It's not touching the surface, right? You see it's not touching the surface. It doesn't have a normal force, therefore. There's no other anything going on. And so we can say this is M, right? That's our mass. And there's no real angles. This is straight up and that's straight down. And so if we wanted, we can set our axes right now. Well, here, I'll do different color. Do white for our axes. And this is probably convenient to say X direction, and then this is convenient for the Y, right? Upwards in the Y direction. Wow, that's sloppy. Alright, so that one we pretty much got figured out so far. So we only have T1, and we want expressions for the tension in each of the 3 chains, and so that's probably our first clue that we're going to need to consider the other body because we don't even have T2 or T3. So we need some expressions for T2 and T3. So let's consider the other body here. So I'll go back to that color right here. So this now is for the O-ring, which usually refers to something rubber, but in this case it is a metal ring in the shape of an O. So what's acting on this O-ring here? Well, one, it's massless, so there's no gravity. It's not contacting a surface, so there's no normal force. But we have the tension from T1, right? We have tension from T2 this way. That's a 2. And we have tension from T3 there. And there's nothing else. So it does say that this here is 60. So now when we're choosing our axes, we want to choose axes that are in line with most of our vectors. So this one's kind of diagonal, but this one's straight left and this one's straight down, so it probably does make sense to have our x direction this way. You could also have positive x that way. You just have to make sure and note that. And you can have positive y down if you want, but I'll just do positive y up, just so I don't forget and make a mistake because of it. Right? These are just things you declare, and you just have to be consistent with your declarations of axes. So it's fair to say that. And so now this 60 degrees deal, if we remember that that's the top surface, right, right here. If that's the top surface, and this was the 60 degrees, then that means that this is also 60 degrees, right? If this is 90, right, and this is 90, you can think of it in terms of triangles. I don't know if that is too confused and written over itself to make much sense, but if you sit down and think about it and verify, you should be able to verify that this angle here is the 60-degree angle. So there we have our the starts for our free body diagram. So we want to find component vectors for this diagonal one here. And so some textbooks suggest that when you write the component forms of the vectors, that you kind of scribble out the main ones so you don't count everything twice. You might find that useful. I'm not necessarily going to do that, but I will do in a different color the component vectors. So the component vector for this T3 would be the component in the x direction and the component in the y direction, right? So if we did this, it's this much in the y and that much in the x. And if our angle here is 60, then what's going on with our component vectors? How can we label this? Well, it's going to be T3. Is it cosine or sine? So here we're concerned with this one here. So it's cosine of 60 degrees. Right? That's the magnitude of this component vector. And so then this one is T3 sine the 60 degrees. Right? Because 60, 60, this is the hypotenuse, so it's directly across from the angle, so we're talking about sine. It'll come faster and faster to you the more problems that you do. But definitely verify for yourself how I'm coming up with that. So there's our free body diagrams. So now we go to step 4, which is to get our equations. So let's see. Step 4. Let's do new color then. Step 4. Get our equations. So we're going to sum the forces in the x and the y for each independently. So for the engine, we have sum of the forces in the x as being, there are no forces on the x, and it's also equal to 0. It's not moving in the x, and so that wasn't much help, but we have it there. And sum of the forces, I'll do it just below. Oops. Sum of the forces in the y. Now we have some forces. So if this is our positive y, and that's our negative y, then we have T1 minus mg. So T1 minus mg. And we're only worrying about the magnitudes here because we already know the direction. We're talking about in the y component. So we don't write them as vectors. And again, it's not moving in the y direction, so we set that equal to 0. So you might be tempted to just quickly get a better equation out of that one, which you could, but let's not get ahead of ourselves, and let's move over to the O-ring. So this is O-ring. What equations can we get about our free body diagram from the O-ring? So again, same thing. Sum of the forces in the x. So what are all the forces in the x? So we have T2 clearly in the x, but we have more than that. We have this component of T3, which we've identified as T3 cosine 60. And that's in the positive x direction. So T3 cosine 60 degrees minus T2. And it's not moving in the x direction, right? The O-ring is stationary. That's why we're using Newton's first law. So it's equal to 0. Objects at rest will tend to stay at rest, no acceleration. Okay, and then sum of the forces in the y. So what's going on in the y? So we have the component of T3 that's in the positive y direction, this T3 sine 60, and we have T1 in the negative y direction. So T3 sine 60 minus T1, right? Yes, 1. It's also not moving in the y again, so objects at rest tend to stay at rest. Acceleration is 0. So there's our 4 equations. I'll move them all into view, hopefully. Not all of them might be needed, but at least we've identified all of them. There's our 4 equations. Okay? So, what are we trying to solve for again? If we go back to our step 1, we're trying to solve for the tension in terms of the weight. In terms of the weight. So I guess here, we don't even need mg because we want it in terms of the weight. So I'll leave it as w. I should have left it as w up here. Because that's what we wanted in terms of. So we'll do that. Yeah? So there's our weight, and we have the rest of our equations. And so now we're on step, what color should we use? Gold. We're on the last step. Go for gold. So we have our equations and we want to solve for the weight. Well, or we want to solve for the tension in terms of the weight. T1 is equal to the weight. That's pretty simple, right? That came from this equation here. Very simple. So if we have that, then we can go over and plug in T1 as being weight over here. So we have, make this nice and big so you can see it. So now we have T3 sine 60 is equal to the weight. And so then T3 is equal to weight over sine 60 degrees. And that's another one. Right? And then lastly, now that we have T3, we can solve for T2 here. So up there, so, sum of the forces in the x, we had this expression, T3 cosine 60 degrees minus T2 is equal to 0. I'll just do this. It's equal to T2, right? Just bring it on over. Now we have an expression for T3. So that means that we have W cosine 60 degrees over sine 60 degrees is equal to T2. And you could call that done, I guess, but we'll say W over tangent of 60 degrees is equal to T2. All right. You should go through that all on your own and verify that I did that correctly, but those are our expressions for each of the tensions in terms of the weight. Tangent of an angle, that's just a number, right? So we can have it in terms of that. That's just a number. It's not an extra variable. We don't have to deal with anything else. We're done. All right. Shall we do another example? Let's. Last example here. So here we have there we go. Let me move this all out of the way. Something involving a ramp. Let's see if that's on the screen. Is that better? Yeah. It's only going to get so good, I promise you. Okay. So blocks of granite are to be hauled up a 15-degree slope out of a quarry, and dirt is to be dumped into the quarry to fill up old holes. So I'll let you read through the rest of that while I situate this picture they show of what's going on. Yeah. So that's what's happening. Looking at my notes, I might have made a mistake on the last one, so definitely go check. Might have made a mistake in the last 20 seconds of that video there, or of that example. So check it for yourself. Find my mistake. Let the student become the master. Okay, so what are we trying to solve on this problem here? How must the weights W1 and W2 be related in order for the system to move with constant speed? So we're trying to find an expression involving or relating W1 and W2, so the weight of the cart and the weight of the bucket, so that it moves with constant speed. We're ignoring friction, and we're ignoring the weight of this cable here. So the way pulleys work is they just redirect the force, and so the force on the cart here is this way, and the force here is this way, right? So there's tension on the cable, and it's just going around the pulley, and so it's pulling on the bucket upwards and it's pulling on the cart towards the pulley. So it's just completely redirects. So let's go back to something like this color. How about that? So step one, what are we trying to solve for? Expression relating W1 and W2. I think it's helpful to just write that out for myself. Or maybe underline it in the problem if you're working on paper. All right, 2, simple sketch. So that's pretty simple. You might be able to just roll with that. I'm gonna go ahead and draw my own anyhow though. We have here a ramp. I'll do this just to show that that is a solid surface there. We have a pulley, like that. We have weight 2, right? The bucket is weight 2. Yes, dirt-filled bucket, weight 2. And then this force over here, weight 1. All right, and then this is 15 degrees. There we go. And that's all we need. None of the rest matters. Don't care about the dirt in the bucket, don't care about the fact that the cart has some rope and some other block on it. That's all we need. All right. So now step 3, free body diagram. So let's go ahead and get that done. Free body diagram, we'll do that in a new color. Let's do this. So we have 2 bodies again, and you probably are guessing that we'll need 2 different free body diagrams, one for each. We can just try one if we are not sure and we don't recognize that right away. And if you come up short on equations and you can't solve for what you need, then you know you have to consider more bodies. And then you get the rest of your equations. So there's no magic here. You just you build an intuition after a while for what you need to directly go to, but you can do some trial and error work if you're not sure. So let's do first for W2. Or what do we do? Yeah, W1, let's do what W1. Why not? All right, so we have the bucket, or the cart, right? So it's gonna have some gravitational force pulling down. We'll just say in terms of the weight, since they seem to be talking in terms of the weight. We'll leave it as that. It's gonna have some tension force this way, right? That's probably a lot too steep for 15 degrees, but you know, it doesn't matter as much. But this would be tension. And then we have some normal force, which is perpendicular to the surface, right? And the surface is parallel to the tension force, right? So the surface is like this, and it's perpendicular to that, so these are perpendicular. And we'll call this the normal force. I'll use capital N here. All right, and is that all that's going on? It kind of is, but let's make sure and include our angle here. So we have this angle 15 degrees. But if we're wanting to choose our axes wisely, two of our forces are perpendicular to each other, and this last one is not. So we could rotate the whole thing, or rotate our axes rather, and help ourselves out. So I'm going to write my axes in line with this thing. We'll make this the positive x direction, and this the positive y direction. I keep doing this to myself, leaving myself not enough room. So positive x, positive y. So now these two we don't have to find component vectors for. But we do have to find component vectors for this weight, because it's the weird one, right? So now do some thinking to figure out if this was if this is 15 degrees, then what is this angle, right? Or what is this angle alternatively, right? Which one of those is 15 degrees? So think about it for a little while. So it's this one, and you might guess by the way that you've drawn it, but even if you've drawn it way off, you should just be able to convince yourself that that is the 15 degrees angle there. And so therefore, if we're wanting to find component vectors, I'll just try to keep consistent and do those in pink, and that means that it would be this much in the negative x direction and this much in the negative y direction, right? Or maybe something slightly less than that much. That's what we're doing there, right? I'll go ahead and try to stop overlapping things. So we have this being the weight of 1, right? Hopefully you can see what's going on. Hopefully the angles are working out okay for you. Okay, so what is the magnitude of these things? Well, it's going to be W1 times either sine or cosine, right? So if this is the hypotenuse, this is the one, the component we want is adjacent, and it's going to be cosine of that 15 degrees. And then this one here, put it down here. That's kind of wild, huh? W1 sine of 15 degrees. Yeah? Does that work out? Do you agree with that? Now let's do our free body diagram for the bucket. Now we have W2 here, free body diagram. So, what do we have going on with the bucket? It's a little bit simpler. We have weight pulling down on it, so weight W2, and we have tension pulling up on it. That's the same tension as before, so we don't have to label them differently. The pulley just redirects. It's not a new rope or a new cable, it's the same cable. So that's all that's going on there. And so if we wanted to choose our axes, we just choose it right in line. You could have the positive y going down if you want. I'll just go up because I'm prone to mistakes otherwise. So that's the x direction. Alright, no need to find any component vectors. They're all directly in line with the y. So step 3 done. Free body diagram done. So now, let's go on to the next step. Let's use that greenish color we came up with before. Or get our equations. So our equations for W1, we have the sum in the x, sum of the forces in the x, being equal to some things, right? And you have to remember what your x actually is. This is the positive x. So we have t minus the component of W1. So we have t minus W1 sine 15 degrees. And that's equal to 0. It's moving, but it's moving at constant speed, so the acceleration is 0. But it is moving, right? So make sure you don't confuse acceleration and velocity. Go back if you need to get a nice clear distinction between the two. And then sum of the forces in the y is equal to y, there's the normal, I think that's still on the screen for you, the normal force is directly in the positive y, so n, minus the component of the weight that is in the negative y direction, which is W1, cosine 15 degrees, and that's also in the 0. It's not moving in the y at all, right? The way we've defined our axes, it's not jumping up off of the ramp, it's not crushing down through the ramp, it's not moving in the y at all. So acceleration is constant because it's 0. All right, and then let's do W2. So here's W2. Our equations come from sum of the x and sum of the y. So sum of the forces in the x, there are no forces in the x. So it's 0. Not very helpful. Sum of the forces in the y, we have t minus, minus W2. And that's equal to 0. It's moving in the y. The acceleration is 0. Its velocity is constant. Acceleration is 0. So we want an expression relating W1 and W2. I think we can get that because here, and let's move over, sure, be consistent, and say we're on step 5 now, doing the easy part and solving. Because look at this one here. T is equal to W2. That gets us that relation. And so then we can go and plug in right there. So if T is equal to W2, then that sum of the forces in the x for W1 means W2 minus W1 sine 15 degrees is equal to 0. Yeah. Right? So W2 is equal to sine 15, and if you actually calculate it, since I wrote it down in my notes, 0.26 W1. It should be going all the way, which is preferred. And so what does that actually mean? What did we solve for? I mean, we did what they wanted, but let's think about what that means to see if that's reasonable at all. Well, that means that W1 is about 26% of W2. And so, or no, W2 is 26% of W1. So that means that the dirt-filled bucket is about 26% of the cart, which seems reasonable to me. All right, I think that's the last example that I wanted to go through. Let me make sure that was my last page. Yes, all right. So next we talk about Newton's second law, when to use it, strategy, go over a few examples as well. Hopefully this was useful to you, and we'll move on to Newton's second law next.